Um, Today's date is the 30th of April, 2026. The time now is 12:02 p.m. So I'm gonna be expressing how I'm gonna make this work for myself. So I'm tripolar, me, myself, and I. And this video is on MMUKO OS, M for Mike, M for Mike, U for Umbrella, K for Kilo, for Oscar. And MMUKO OS, M for Mike, M for Mike, U for Umbrella, C for Charlie, O for Oscar. The Miko OS, naming convention, everyone is standardized. So Muko and Muko OSs. So the integration between the physical and the digital world that kindness and bind us all. Today I'll be computing. Today I'll be expressing computation as a series of basically the spin system. So we have half a quarter spin. Last video I made is basically if Uche, if Eze and Obi share Eze and Obi share a half spin, a quarter spin, no, a quarter spin, one divided by four, one divided by four. We have Eze. So if there are two poles, Eze's pole represent consensus. Yes, no, maybe, maybe not. And yes, no, maybe, maybe not represent two distinct poles, two different poles consensus, a trinary consensus logic of every pathway should we go. There's Eze can make a decision, can set permission, give permission, but it's no computation on analysis. Now, this can represent accounts or login credentials, login to MucoOS. So, how do you log into MucoOS? Now, the beauty of this is MucoOS is a cybernetic interface. What that means is that MucoOS, M for Mike, M for Mike, U for umbrella, K for kilo, O for Exa, expresses uh, have a stability map onto the real world. So, so basically, my goal is to log in with my hand on the GitHub repository. GitHub repository. So, log in with my hand. Let me try to find the documents. MUKO OS exhibit pseudocode MUKO boot. So this is a MUKO boot sequence. This is supposed to be MUKO, and this is meant to be MUKO. Require hands of magic. You know. So we got the MUKO boot sequence here. But there is yes, here it is. Here it is. So you have in the file system, you have a system of tree self-balancing trees. They can rotate, but everything is aligned to the center. So the trunk goes here, trunk goes to side. Because you have a system, you have a ring indexing system, ring indexing or system. So today I'm trying to express how to compute on a MucoOS. So MucoOS gives you a qubit. So you have a qubit for everything in model. So what does a qubit represent? 1 second. The qubits, C for Charlie, B for Bravo, I for Indigo, C for Charlie, B for Umbrella, B for Bravo, I for Indigo, T for Tango, is a computation of a compass ring, of a compass, a classical bit, and a quantum system. A quantum system, a quantum bit, and a classical system. Mathematically, it's the idea that we have qubits for anti-corruption. We could quote it directly, but the system is basically have to build for the human rights whole system. So you're gonna have half 1/4 plus 1/4 equals 1/2. Am I right? 1/4 plus 1/4 equals 2/4, which is 1/2. This two half poles represent a vector in vector space in linear span in a linear vector space, a span in a linear arbitrary vector space. My point is to compute with vectors. Basically, I'm not giving you the wrong idea. I'm giving you a mathematical model for how the system operates. So doesn't matter what as you're playing in computing, you are computing on a qubit. And I want to see what you can get by computing on a qubit. So when your system is initialized, you use it's free from corruption until you have qubits like memory compression, because until you have because it was on compass ring qubits, compass ring. So because everything lies to the center, everything has a common middle. The shear space, you know where the center is, know where the medium is, and middle is. So mathematically, you get one half, and if SA owns 1/2 memory, it will be even 1/2. We have 1/2 plus 1/2 plus 1/2, and or 2/3. 2 times 3 is 6. 2 times 3 is 6. 6. 1 times 3 is 3. 3 times 2 is 4. 4 6. So we have the ratio of 3 6 and 3 6 and 3 6 and 4 3 6 4 4 6. So I'm expressing that one if the pole of each essay is of a pole of a computer of a pole representing the consensus pole, like has 1/4 plus 1/4, it gets equals to 1/2. Now 1/2 is basically what they have together. But there's how many ring states on it? So you're gonna have spins of half spin. These are the compass spins. So you don't very important you understand mm, very important you understand the read write execute permission tree works on compass ring. So I'm trying to express that any kind of computational operation is a spin. Any kind of computational operation is a compass spin. So if I'm performing a read, so one half state of a system replaces the spin because it's not so to keep it anti-corrupted. So to keep it the system respect its own principles. The qubits facilitate basically the qubits has to use the kind of qubits to do some computation. So for example, if I want to add two binary numbers, and if I want to multiply two binary numbers with memory in the computer, with say I have two binary numbers expressed as 52 and 46. That might actually be that will be in the tens. So you can take this number and go to general. So 55, 50, 50 is just two is just a unit, 2, 0, 1, and 50 will be a tens 50 will be a tens of 10 and 50. That will be 5, but with a 10 unit, that will be 10. So example, we go to compute on using spin. So, using the kind of philosophy of the operating system. So, any kind of spin, so I'm demonstrating here, I'm trying to demonstrate on my paper here. I'm trying to demonstrate that this is all possible to compute with the spins on the classical system. But these spins are what MUKO really gives you as part of the MUKO library. So the MUKO library is literally the spin architectural pattern used to design a rainbow system, and that's referring to all philosophy. So you can compute. Doesn't matter where you compute because the reference to computing operation. Doesn't matter if you're sending a file, sending an email to NASA. They work on quantum spins, and those quantum spins are like classical systems. So also the magnetic memory is a runtime update. It's like it operates in runtime. There's some answer. So where did I stop? So the first step of this problem was the first problem I defined was like a half plus half equals a quarter plus a quarter equals one half. Now one half will have two thirds have another one half not allocated, and this one half is really so two thirds two thirds is delegated to it's going to trinary, going to trinary logic. So if you have one half plus one half, you have one half times two thirds. You have two thirds is dedicated to Obi. I mean Eze and Uche. So this is another pole. So this is another pole of the system. So by respecting the principle of the computer via trinary consensus, you have three states that preserve at all time. You know, so that's the goal. So you have to try to have the yes, no, and maybe not and maybe of consensus. So you can always have consensus in the framework of the framework. So in the framework, so so you have two thirds left. Two thirds is just two thirds. You're gonna have one minus two thirds will give you or four, one or four over four minus two thirds, will give you two. Four minus two is two. Four minus three is one. Two over one. Two divided by one. And if or one two divided by one. So you have a memory that you can compute over. So you have a resource that you can never lose. That if based on trinary consensus. So this mathematical will demonstrate. So I'm demonstrating that this works mathematically. So again, so we started with this will again a very short video by the way. So we started with one half, one quarter plus one quarter equals one half, and then we conclude them because that one half was that Eze and Obi using the computer or two people, two parties, two bilateral consensus system. If they are working, when they in the worst case, if they're working together, in the worst case, in the average case, when they're working together. So by expressing that's the average case when they're working together, you know, you're gonna have a low depth, but you have Uche's fault. So you gonna because if X says no, yes, and Uche says no, this results in a yes times no is maybe. The maybe is delegated to another system called Uche. Now, Uche is another person in consensus that has another vote. So if Uche joins the vote, Uche now joins to trial as a consensus system from yes, no, and maybe. So you have trial as consensus of Uche's poll making it two thirds. Two thirds. So you have one quarter, one half plus one half equals one. One half. One quarter plus one quarter equals one half. One minus one half is one half. You have one half, but this one half is basically in the what Uche can have. Uche can have is one half, but if Uche only needs two thirds of information, two thirds one minus two thirds is one minus two thirds of four divided by four minus two thirds equals to equals to uh two over one. Two over one. Now, two over one represents a pole of Uche. 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 Now, Uche's pole is two thirds. By having a two thirds pole, he has a two third consensus pole. So Uche can make a guess where the two thirds comes from. So you get OB. So basically, the two thirds represents operation of consensus. So you're gonna have one quarter, and two thirds. As a trinary spin state, Now, this trinary spin state is a consistent because it's basically a trilateral system. There are three parties involved in the making decision of a system. So it's like it's like an admin system, and it's basically administration system. So you have a computation operation. Everyone has space on a disk drive, to com- to make informed decision about a role in a kind of a constitutional role via openness design and computing, design and technology. Openness is design. Basically, design is like not an initiative. It's basically a particle of design and technology, design and technology. So the goal is to have the roles for the tree via roots, via ring boot topology. Have based on the cubic model. So so 1/4 plus 1/4 equals 1/2. 1/2 plus 2/3 equals 3/5. No, you can't add them together because different. You have to times them. Equals 3/5. Yes, equals 3/5. But if you multiply them, basically this represents three fifths. So 3/5 of an operation is what is consumed. No, this is spin, but you don't add the spin. So you're gonna have spin. So you multiply the spins because spin can be spin up, spin down. Spin up, spin down. What represents like opposite conjugate spins, which have negative operands involved. So opposite poles. So you're gonna have spin up, spin down. This is complex ring system. So today's video has been very explanatory, but it's a very important philosophy that you can always use in qubit models to compute on a quantum system. So you can use expressions of a quantum ring to compute on a cybernetic interface. And cybernetic interface is basically the what you see on the computer. So but the goal of the video was to try to use my hands try to use my hands to log into to create a login system, to log into my operating system. So this is basically called a signal. So to take my finger and trace the path on the operating system with my camera to log in, or to show my hands and just a kind of sign, peace sign to log in. I hold the peace sign for 3 seconds. So you have like a final consensus to log into the computer. So that was why the spin states matter really. But there's spin states that hold information, hold context via consensus. They hold context. You don't need to hold it, but the computer holds it for you until you have example application. So if I have my hand, my pen just dropped. If I have my hand here and the my finger will get and I put my hand on the camera, and the say log in, and log in, draw your signal. I take my finger, I lift it, I draw, I trace the path, you know, and that path is just me drawing with my hand, with my tip of my fingers. That's what we should log in, because I draw my signal like like an artboard, and so I can continue from where I made a mistake. So if I cannot draw my signal, it will return me back to a staleless state, a staleless. The key word here is staleless because a staleless system allows you to be still. Like it's not a, it's a, it's a staleless. It remembers the context it was at, but he doesn't remember. If you mess it up too much, it is still less. So this is if it's ability or not can continue from where you last draw with your thing, where you trace with your path. So this is how to log into your MMUKO. Let me try and give you example. Give myself an example here. So this is my signal. Let me draw it here. No mistake. Two, three, four, five, So this is my signal. So this is my signal. This is how I log in. So this is why I would trace my computer. Any kind of arbitrary symbol I make on this kind of process, like my like children. So like anytime I trace. So basically, I start from here. I can trace out with my hands. So it's a stateless login system. I'm using here because it's like a child remembers the last information you said to it, without the context, because that was where you stopped. Because the spin states are preserved as part of the process, So if I draw any kind of arbitrary shape, when I pick up my pen, when I pick up my stylus, I pick up my hand, is where I continue. All I have to do is just take my computer to pause, put my hand in front of the computer and log in. For example, for example, I put my hand here and it says 5, 4, 3, 2, 1, draw your login signal. I take my hand, I go right, left, right, right, left, left, and then right, right, up, up, and then do my you know, circle as one go. So basically I do my loop, 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 and it's done. So this is how I log into my computer. So it's basically a service that you log with your hands. You go to log in with your hands and log in with your, it's gonna be part of the MMUKO key ring, based on your from. So, you're gonna be logging into the system. It's basically based on evil philosophy, but the goal is to have a stable system. Like it doesn't expire. It doesn't expire. Stainless means it does not expire. It cannot expire because the state is preserved when you pick up your pen. So it's a Hamiltonian system. Unless you make a mistake and you can't log in, or you pick up your pen, you can continue from where you put your pen down. So that's the idea. So it's like, tracing a path. So a path is basically the same thing. So it remembers the state it was in. So if you have a pencil, like I did with a pencil here, I've demonstrated that, this is like a login, this is my own login. But if I can draw this login, the computer will remember the path it took to where I stopped. So if I stop at a junction, like a right angle, and if I stop at the center, like if I try to draw a line, this is a very easy one to do. But you can have all kinds of zigzags to kind of shape. You can put your signature down. So this is like my signature, to log in to my computer system. But the goal is to have a something that you do with your own body. You are the controller. So you're gonna have it with your controller. You can use your retina to do it. You're gonna use your controller to do it. Your body's controller. That's the idea. So of the three rules play like how to log into your OS that never expires. Uh, uh, you can turn. You can't. Something tells you I shouldn't make it turn it offable. Okay, you can't turn it off. It's on by default. Because it's a stateless protocol. So I'll make it on by default. As I also state. Thank you for watching this video.